Deep within the unassuming plastic shell of your phone charger, a tiny silicon chip hums with more processing power than the entire guidance computer that navigated the Apollo 11 mission to the moon in 1969. It is a strange, almost surreal realization to think that the technology we use to scroll through social media is hundreds of times more capable than the machine that first carried humanity across the cosmic void. Back then, the engineers at NASA didn't have the luxury of modern microprocessors. The heart of their computer wasn't etched onto silicon, it was literally woven by hand. They hired skilled seamstresses who used needles and copper threads as thin as a human hair to stitch the flight code through magnetic rings, a 1 if the wire went through, a 0 if it went around. It was a masterpiece of manual labor, nicknamed Little Old Lady Memory. If a single person had sneezed and misplaced a stitch, the entire mission might have ended in disaster. Yet, this hand-woven computer guided 3 men sitting atop 3,000 tons of high-explosive fuel across the silent vacuum to a desolate gray sphere, allowed them to collect a few bags of rocks, and brought them home with the precision of a routine business trip. Half a century later, we find ourselves in a peculiar position. We have artificial intelligence that can write poetry and algorithms that predict our every move. Yet returning to the moon has proven to be far more difficult than assembling flat-pack furniture. As we look toward the upcoming Artemis II mission, we are reminded that gravity and the vacuum of space do not care about human ego. In recent years, our attempts to return have been marked by high-stakes drama. We've seen landers crash at hundreds of miles per hour, inadvertently turning the lunar surface into a graveyard for dehydrated tardigrades, and sophisticated robots lose their way because of a single line of logic in their software. There is a haunting sense that we have spent 50 years becoming smarter, yet we have forgotten the ancient craftsmanship of the Apollo era. We didn't just lose the blueprints, we lost the hands that knew how to build them. The Apollo spacesuits were sewn by workers who usually handled lace and undergarments, requiring 21 layers of precision where a single pinprick meant death. Today's automated factories would tear those delicate fibers to shreds. We are realizing that the first moon landing wasn't a casual conquest, it was a quiet intrusion into the lair of an ancient beast while it slept. Now, as the Artemis II crew prepares to venture back toward that lunar horizon, the mission isn't just about national pride, it's about survival and resources. To get there, we must face the tyranny of the rocket equation, a fundamental law of physics that dictates a cruel price. To lift a tiny amount of weight into space, you must carry a mountainous amount of fuel, which in turn requires even more fuel just to lift the weight of the fuel itself. This is why modern designs like the Starship are so revolutionary. Instead of trying to carry everything in one go, they act like a celestial logistics company, using orbital gas stations to refuel before the long trek. It is a gritty, practical approach, a world away from the poetic elegance of the 1960s, but perhaps more sustainable. We are moving from the era of heroes to the era of cyber delivery drivers, where it's okay if a robot tips over or breaks a leg upon landing, as long as it gets the job done at a fraction of the cost. The destination has changed, too. We are no longer aiming for the flat, sunny plains of the lunar equator. Artemis II and the missions that follow are setting their sights on the lunar South Pole, a place of extreme physical contrasts. There, you find the peaks of eternal light, where the sun never sets, and right next to them, craters like Shackleton, where the sun hasn't shone for billions of years. In those permanently shadowed depths, temperatures are colder than the surface of Pluto, dropping to a bone-chilling level where molecules almost cease to move. In that absolute silence, hidden within the frozen soil, lies the ultimate prize, water ice. In the context of deep space, water is more than just a drink, it is the gold of the solar system. It can be broken down into hydrogen and oxygen, the very breath of life and the fire of rocket fuel. By reaching these dark craters, we aren't just visiting a monument, we are building the first gas station in the stars, securing the gateway to the rest of the cosmos. As you drift toward sleep, imagine the Artemis II capsule gliding through that velvet blackness, carrying us back to that ancient, frozen treasure chest, bridging the gap between the hand-woven dreams of the past and the stainless steel future of tomorrow. If you take a simple molecule of water, 2 parts hydrogen, 1 part oxygen, and pass an electric current through it, you unlock the most potent chemistry in the cosmos. By separating these atoms and chilling them into their liquid state, you create deep cryogenic rocket fuel, liquid hydrogen for thrust and liquid oxygen to sustain human breath and fire. In the airless void beyond our atmosphere, water is no longer just a refreshment, it is a synonym for power, for sovereignty, and for a return ticket from the red deserts of Mars. To hold the ice hidden in the shadows of the Shackleton crater is to hold the keys to the solar system's new Persian Gulf. For decades, the script seemed simple: the moon was a bone-dry desert, save for the dark, frozen pits at its poles where empires would eventually clash for resources. But the universe has a way of rewriting our textbooks with a touch of cosmic irony. In 2020, a modified Boeing 747 known as Sophia, a flying infrared observatory, pointed its massive telescope toward the Clavius crater. Unlike the dark pits of the South Pole, Clavius sits in full view of the Sun, baked in temperatures exceeding 100 degrees Celsius. According to every known law of lunar physics, any water there should have evaporated instantly. Yet, Sophia's sensors captured the unmistakable signature of $H_20 molecules, not as pools of liquid, but as tiny treasures locked deep inside mineral crystals and microscopic glass beads. Shortly after, China's Chang'e 5 mission returned to Earth with fresh lunar soil, confirming this strange reality. Under the microscope, scientists found billions of tiny glass spheres. These glass coffins were forged by the sun itself. For eons, the solar wind has bombarded the moon with high-speed protons, essentially hydrogen nuclei. When micrometeorites strike the lunar surface at 10 times the speed of a bullet, the resulting heat melts the rock into liquid droplets. In those frantic milliseconds of impact, the solar protons bond with oxygen atoms in the lunar soil, creating water that is instantly sealed inside the cooling glass. The moon, it turns out, is a giant, greedy sponge, absorbing the very radiation that tries to dry it out. However, the universe pairs this discovery with a bit of cold humor. While the water is there, the moon remains 10 times drier than the most scorched heart of the Sahara. To extract enough water to fill a single coffee cup from the sunlit soil, an astronaut would need to process an entire truckload of lunar regolith in an industrial-grade microwave. You are standing on a massive reservoir, yet you must move a mountain for a single sip. This scarcity has ignited a high-stakes land grab 38,000 kilometers away. As the Artemis II crew prepares to orbit the moon, they are the vanguard of a new era where international law is being tested in a lawless frontier. The Outer Space Treaty of 1967 high-mindedly declared that no nation can own the moon. It was a beautiful sentiment from an era when no one could actually stay there. But today, the legal fine print is being scrutinized. While you cannot own the land, the law is silent on the resources you extract. It's the loophole of the century: you don't own the orchard, but the apples you pick are yours. This has led to a sophisticated game of safety zones. Nations and billionaires aren't planting flags to claim territory anymore, they are landing expensive, delicate hardware near the best water-rich craters and politely telling everyone else to stay 50 kilometers away to avoid interference. It is a first come, first served law dressed in the lab coat of scientific cooperation. The competition is already crowded. In 2023, India's Chandrayaan-3 proved that a modest budget could achieve what was once the sole domain of superpowers, landing precisely near the southern latitudes. Japan's SLIM mission, despite landing upside down in a moment of technological dark comedy, proved that we can now snipe a landing spot with the precision of 100 meters. Meanwhile, China's Chang'e 6 recently performed a masterclass in robotic engineering, retrieving soil from the hidden far side of the moon, a place where communication is a nightmare and the terrain is treacherous. The maps of NASA's Artemis II and China's future lunar stations are already overlapping, focusing on the same few sunlit ridges near the South Pole. But as politicians and moguls divide the lunar map, the moon itself remains a silent, patient killer. To step onto its surface is to enter a world designed to dismantle the human body. Without the heavy blanket of Earth's atmosphere, the vacuum of space executes its laws without mercy. If you were to stand unprotected on the moon, you wouldn't explode. Instead, the lack of pressure would cause the moisture on your tongue, in your eyes, and in the linings of your lungs to begin to boil at body temperature. Within seconds, the vacuum would pull the oxygen out of your blood in a process of reverse respiration, leading to a quiet, hypoxic unconsciousness. To survive, we wrap ourselves in human-shaped spacesuits, but even these high-tech cocoons are vulnerable to the moon's most pervasive threat, the dust. Lunar dust is not like the soft sand of a beach. On Earth, wind and water smooth the edges of rocks over millions of years. On the moon, there is no erosion. The regolith consists of microscopic shards of volcanic glass, jagged and sharp as razors, forged by billions of years of meteorite impacts. Because of the constant bombardment of solar radiation, these shards are statically charged, clinging to everything they touch. They don't just sit on the ground, they levitate in a ghostly, low-gravity haze. This dust acts like industrial sandpaper, grinding away at the seals of spacesuits, jamming the joints of robotic rovers, and threatening to shred the lungs of anyone who accidentally tracks it back into a habitat. As we look toward the moon tonight, we see more than a poetic nightlight, we see a jagged, radiant, and frozen frontier, a place where the water is locked in glass, the gas stations are hidden in eternal darkness, and every footstep is a battle against the fundamental laws of physics. We are returning to the moon, not as casual conquerors, but as fragile guests in a magnificent, lethal wasteland. When Eugene Cernan, the last man of the Apollo era, finished his final moonwalk, his spacesuit was a battlefield. The joints were so clogged with dust they could barely move, and his hands were rubbed raw and bleeding from fighting the stiff, frozen pressure of his gloves. In that silent wasteland, you don't need a giant asteroid to end a mission. A single grain of jagged glass caught in a rubber seal is enough to turn a triumph into a tragedy. This is the reality of the moon, a world of microscopic razors and impossible extremes. Once you survive the physical abrasion of the dust, you face the second test, a total lack of thermal control. On Earth, our atmosphere acts like a soft, weighted blanket, distributing the sun's heat evenly. But on the moon, the thermostat is broken. Because there is no air to hold or move heat, the temperature depends entirely on whether you are standing in a shadow. At the lunar South Pole, the sun hugs the horizon like a pale, ghostly lamp. If you were to crack an egg on a sunlit ridge, it wouldn't fry. Instead, the vacuum would flash evaporate its moisture so fast that the resulting chill would freeze the egg into a brittle, gray sponge in seconds. In the light, it is a manageable 0 degrees, but step just 1 inch into the shadow of a boulder, and the temperature plummets to -230 degrees Celsius, twice as cold as the deepest winter in Antarctica. You are effectively standing with one foot in ice water and the other in liquid nitrogen. To survive this, a modern spacesuit must be a perfect, wearable thermos. Inside the suit, nearly 100 meters of tiny plastic tubes circulate cooling water around the astronaut's body, while the outer layers consist of over a dozen sheets of aluminized film designed to reflect the sun's radiation like a high-tech mirror. During the Apollo years, these suits were so bulky that astronauts looked like the Michelin Man, moving with the stiff, jerky grace of a rusty robot. If they tripped, it became a clumsy comedy of errors as they struggled to regain their balance in 1/6 gravity while carrying a massive life support backpack. But for the Artemis era, where we plan to stay and build, we need more than just survival, we need mobility. This is why NASA partnered with Axiom Space and, surprisingly, the luxury house Prada. This isn't about fashion, it's about 20 years of Prada's experience with high-performance carbon fibers and seamless weaving for elite yacht racing. They are crafting an outer shell that is white, smooth, and incredibly tough, a high-fashion armor designed to repel static charge dust and allow an astronaut to crouch, bend, and work with the precision of a craftsman. But even with the best suit, you eventually need a home. Shipping building materials to the moon is a financial nightmare. At over $1 million per kilogram, a single red brick from Earth would cost $3 million just in shipping fees. To build a city, we must use the dirt beneath our feet, a process called in situ resource utilization. Lunar soil contains tiny, nanophase particles of pure iron, forged by billions of years of meteorite impacts. These metallic specks make the soil a perfect absorber of microwaves. In the future, a robotic 3D printer will crawl across the surface like a mechanical beetle, using high-power microwaves to melt the regolith into a glowing, molten lava. This liquid rock is then extruded layer by layer, cooling slowly under a protective hood to prevent it from shattering in the extreme cold. The result is a solid, black, glass-like dome, a lunar igloo that can shield humans from DNA-shredding cosmic rays and micrometeorites traveling 10 times faster than a rifle bullet. Inside these glass domes, we will have to solve the problem of hunger. In 2022, scientists managed to grow a small, hardy weed called Arabidopsis in just 12 grams of original Apollo soil. The plants survived, but they were miserable. Their leaves turned distressed, purplish-black as they struggled against the toxic heavy metals and the sharp, nutrient-poor glass shards of the lunar dirt. They were tiny, deformed survivors, but they proved that carbon-based life can, with enough grit, take root in an alien world. To connect these gardens and habitats, we won't use trucks with tires that would be shredded by the dust. Instead, DARPA is exploring a magnetic levitation railway, a silent, frictionless train that floats above the surface, carrying liquid fuel and oxygen between bases without ever touching the deadly soil. Yet, as we synchronize these maglev trains and communicate with Earth, we run into the final, most invisible wall of physics, time itself. According to Einstein's theory of relativity, gravity warps time. Because the moon is much less massive than Earth, its gravity well is shallower, meaning time actually flows slightly faster there. Every single day, a clock on the moon gains about 58.7 microseconds compared to a clock on Earth. It sounds like nothing, a fraction of a blink, but in the world of high-precision navigation, 58.7 microseconds is a disaster. If a lunar GPS doesn't account for this relativistic shift, a cargo ship could miss its landing pad by hundreds of meters after just one day, crashing into the darkness of the Shackleton crater. We are currently building a lunar coordinated time to bridge this gap, a new heartbeat for a new world. We endure the razor dust, the liquid nitrogen cold, and the warping of time for one simple, brutal reason: physics. As the visionary Robert Heinlein once said, once you reach low Earth orbit, you are already halfway to anywhere in the solar system. The moon is our stepping stone, our refueling station, and our first true home among the stars, and the Artemis mission is the first breath of that future. This isn't just a bit of literary flair, it's a precise indictment of gravity, the most uncompromising tyrant in physics. Earth is a staggering 60 sextillion-ton sphere of rock that has warped the fabric of space-time into a deep, inescapable well. Everything we know from 200-ton blue whales to our gleaming skyscrapers is pinned to the bottom of this pit by relentless force. When you stand on a scale in the morning and sigh at the number, you shouldn't blame the calories, you should blame the abyss beneath your feet, trying to pull you toward the center of the world. To leave this well, you must pay an energy toll so steep it would give any space agency's financial director a heart attack. Consider a journey to Mars. It's split into 2 acts. Act 1, igniting the engines to crawl out of the gravity well to low Earth orbit, just 400 kilometers up. Act 2, gliding through 200 million kilometers of vacuum to reach the red planet. Instinctively, you'd think the 200 million kilometer trek is the expensive part. But the cold logic of physics says otherwise. To climb those first 400 kilometers, you must accelerate to Mach 25, a velocity increase of about 9.4 kilometers per second. That vertical sprint of a few minutes costs more in fuel than the entire 200 million kilometer glide to Mars. Earth is a dry well, and we are hikers who realize we have to eat 90% of our supplies just to climb over our own backyard fence. To break this cycle, we've stopped trying to flip the wall with brute force. Instead, we are building the gateway in lunar orbit. It follows a highly elliptical path called a near rectilinear halo orbit, swinging between 3,000 kilometers above the lunar North Pole and 70,000 kilometers above the South. This orbit is a legal loophole in nature, it's never eclipsed by the moon, meaning constant solar power and 24/7 communication with Earth. More importantly, it's a gas station outside the heavy tax zone of Earth's gravity. By launching empty Mars ships to the gateway and refueling them with liquid hydrogen and oxygen extracted from the ice in Shackleton crater, we bypass the gravity tax. The fuel savings alone are enough to fund dozens of new launch centers. This is why nations are clashing over the lunar South Pole. They aren't fighting for a photo op. They are fighting for the only franchise rights on the solar system's first interstellar highway. Yet, as the first ship fueled by lunar ice slowly pulls away from this deep space toll booth, leaving Earth's gravity well behind, the victory feels bittersweet. We've solved the physics, but the biological trial is just beginning. We can build hulls out of titanium and polymers, but we cannot rewrite the fragile carbon and water code of the human body. As these explorers venture into the deep space radiation environment, the biological clocks in their marrow and DNA begin a cruel countdown. And if you think humanity will be content sitting in a black glass dome on the moon, eating stunted, metallic-tasting weeds, you've underestimated our restless spirit. Even as a commander stares through a viewport at the approaching red disk of Mars, they are preparing for a new set of physical punishments. Mars has less than 1% of Earth's atmospheric pressure, and its soil is laced with perchlorates, toxic chemicals used on Earth to make fireworks and rocket fuel. The Martian surface is, quite literally, a global powder keg waiting for a spark, shrouded in dust storms that can blind the entire planet for months. Half a century ago, Harrison Schmitt sneezed inside the Apollo lunar module because the dust smelled like spent gunpowder. Soon, the first Martian settlers will repressurize their airlocks, weary and dusty, and they too will let out a loud sneeze. They'll rub their red noses, smelling the metallic, rusty scent of the Martian plains, and immediately key their radios to argue with Earth. They'll debate whether the real estate in Valles Marineris has better views than the iCities Planitia, or how many nuclear warheads it would take to warm the poles just enough to finally take off those cursed, heavy space suits. We have paid the toll to leave the well, and while the frontier is toxic and cold, the conversation has already shifted from how do we survive to where do we build. That is all for today's journey. May your dreams be vast and your day be bright. Until next time.